Hello everyone, welcome to the video. Today we are going to solve the problem number of ways to make coin change. In this problem, we are given an array of integers. Every element of this array represents a denomination of a currency. For example, here in this coins array, we are given 1, 2 and 3. That means we have 1 rupee coins, we have 2 rupee coins and we have 3 rupee coins. We are also given that we have infinite supply for each of the denomination. That means we have infinite 1 rupee coins, infinite 2 rupee coins and infinite 3 rupee coins. Along with this coins array, we are also given a target sum. And we have to return the number of ways we can make this sum using the coins given in this array. So for example, here the answer is 4 because there are 4 ways of making the sum 4 using these coins which are seen here. We are going to solve this problem. We will go through the thinking process, we'll write the algorithm and then we will also see a working code for that algorithm. Later, we'll also see how to return the actual ways and not just the number of ways if asked as an extension to the problem. So before we start, if you are new to this channel, please don't forget to subscribe and press the bell icon. Let's start. To begin with, let us first note down the key things given in the question. We are given an array of coins. Its size is n, and every element of this array represents different denominations of a currency. We are also given a sum that we have to make using these coins. We have to return the number of ways that we can use to make this sum using these coins. And we are also given that each of these coins we have in infinite supply. So if we consider an example, let's say we are given 1 rupee coins, 2 rupee coins and 3 rupee coins in infinite supply. And we have to make the sum 4. Then what will be the total number of ways? The total number of ways will be 4. Why? Because we can pick all 4 as 1 rupee coins. We can pick 2 1 rupee coins and 1 2 rupee coin. We can pick 2 2 rupee coins. We can pick 1 1 rupee coin and 1 3 rupee coin. Therefore, there are 4 ways of making the sum 4 using these coins. So if we consider our solution as a black box, we are getting as input a coins array as input, its size n and a sum that we have to make. And we have to return the number of ways of making this sum using these coins. So what will our function signature look like? Our function signature will look something like this. Let's start thinking about the problem. Since we can't think of any straightforward way of solving this problem, let us see if we can solve this problem using recursion. That means we first need to identify the just next smaller problems, and then we need to check if we can use the answers to these problems to derive the answer for our larger problem. So let's say we want to make the sum 4 using these coins 1, 2, 3. Now let's say I pick up the coin 1 rupee coin first. Then what do I have? Now if we have picked 1 rupee coin, then we are left with rupees 3 only. That means now we need to find out what are the number of ways of making change for 3. Now let us say somebody comes and tells us this. Somebody comes and tells us that there are m number of ways to make change for rupees 3. Now can we use this m to derive the answer for our original problem sum equal to 4? We may think yes, that if we are given the number of ways to form 3, in each of those ways, if we just add a 1 rupee coin, then we will have the sum 4. So the answer for 4 also becomes m. But this was just one way of breaking this problem down. Instead of picking a 1 rupee coin, we could have also picked a 2 rupee coin or a 3 rupee coin. In that case, our smaller problem would have corresponded to rupees 2 and rupees 1. And let's say somebody gave us answer to these and this as well, n and o. Then answer for 4 as per this will be n and answer for 4 as per this will be o. Now, using this, what should be our answer for 4? Intuitively, it may seem like that since we are looking for number of ways of forming 4, we can just sum these up. So, it will come down to m plus n plus o. Now, is this our answer? No, it won't be our answer, because here we will have many duplicate ways that will be part of this and this, or any of the two of them. Consider this here. Here we have picked a 1 rupee coin and we were looking for number of ways to make 3 rupees 3. Now one way of making rupees 3 is just picking a 3 rupee coin. Therefore, one of the m ways here will be a 1 rupee coin and a 3 rupee coin. Now consider this. Here we have already picked a 3 rupee coin and now we are looking for number of ways to make 1 rupees. Now one way of making rupees 1 is just picking up 1 rupee coin. Therefore, one of the ways among these O ways will be picking up one 3 rupee coin and one 1 rupee coin. Now aren't these two ways same? But we will count them as different if we go through this path. And similarly, if the input is large, there will be so many duplications among all the ways of breaking down. Therefore, it doesn't look like that we have a very easy way of using the answers to these smaller problems to derive the answer for larger problem. That means we have to look for some better way. Let us think in a different manner. Let us say that these are all possible ways through which we can make a sum using some coins. This is the first way, this is second way, this is third way, and so on. So the count of all of this is our final answer. Now pick any one of them, any one way here. We can say one thing for sure. This way will either contain the last coin or it won't contain the last coin. And we can say this for each one of these ways. Each one of the way either contains the last coin or it doesn't contain the last coin. So we can say that the total ways that we are looking for, the answer we are looking for, is equal to ways that include at least one last coin plus ways that don't include even one last coin. This is a fair statement to make. Consider this example. We have to make change for sum equal to 4. And what is the last coin? The last coin is valued at 3. Now what are the number of ways that include at least one last coin? This is equal to 1. How? This 1, 3 includes at least one last coin. Then what are the number of ways that don't include even one last coin? It is 3. How? Because all of these 3, 1, 1, 1, 1, 1, 1, 2 and 2, 2, none of these 3 include even one coin of rupees 3. And therefore 1 plus 3 equals 4. Now that means we have a way of breaking our problem down. We can say that total number of ways is equal to number of ways that include at least one last coin plus number of ways that don't include even one last coin. Now let us see them one by one. First, let us consider the inclusion one. Let us say we have n coins. Then when we are talking about the include part, then our smaller problem gets reduced to forming the sum minus last coin value using n coins. Why do we say that? Because we have to include at least one last coin. Therefore, now the sum that we want to form is reduced and we can form this using all n coins that we have. Let's see what happens in the case of exclude. If we are sure that we are not going to include the last coin even once, then our smaller problem becomes that we have to form this value sum. Still we have to form the value sum, but using only the first n minus 1 coins. Because for us nth coin does not exist. We won't even use it. Therefore, if in case of this example, for the exclude case, for us this array 1, 2, 3 is as good as 1, 2 only, because in the exclude case we won't use 3 at all to form the value, to form sum. Here we had two inputs. First the coins array and then the sum. Now in the first case of include, our sum got reduced. So our smaller problem became because our second input got reduced. While in the second case, the exclude one, sum remained same but our coins got reduced. So our first input got reduced. So that means we have expressed our original problem in terms of two smaller problems. In one case, second input got reduced. In one case, first input got reduced. Now, if somebody comes and tells us the answer to this smaller problem and the answer to this smaller problem, can we use these answers to derive the answer for our original problem? Yes, it is a case of simple addition. If we add these two answers, these two smaller problem answers, we will get the answer for our original problem. That means we are solving this problem using recursion. This include-exclude technique is very common and is used in multiple questions. Let us now try to represent our original problem and our smaller problems as inputs to one common method that we will be calling recursively. So if we are representing our original problem as number of ways to form sum using first n coins, then how will we represent our first smaller problem? It will be number of ways of forming sum minus last coin value by using first n coins. Similarly, how will we represent our second smaller problem? It will be number of ways of forming sum but using only first n minus 1 coins, and summation of these two will give the answer for our original problem. Now this is a recursive relation because we will be calling this same method again and again. So since this will be a recursive method, this is a separate method than our main method. From our main method, we will call this first with n and sum, and then recursion will take care of the rest. We can use this recursive relation to now write the algorithm. Let us now try to write the algorithm for it using this recursive relation. As with any recursion problem, we will go through this step by step. We have already done the first two steps. We have identified the recursive relation and we have identified what will be the inputs to that recursive method call. So therefore our recursive method call will look something like this. This will be the signature of our method. It will take input as n, it will take input as sum, and it will obviously have input as the coins array because we need this array to figure out the value of the last coin. So what does this method call denote? It denotes that it will return the number of ways of forming the sum using first n coins itself. Let us now use this recursive relation to fill out this algorithm. So we clearly need the last coin value as per the recursive relation. And what will be the last coin value? It will be coins n minus 1. Now let us try to form what will be our include answer. Our include answer, where we include at least one last coin, will be NOWSUtil coins n sum minus last coin value. And similarly, our exclude answer, where we don't include even one coin of the last coin, it will be NOWSUtil coins n minus 1 comma sum. That means form sum using only the first n minus 1 coins. And here it means form this value using n coins. And our final answer will be the sum of the two, so we will return it. But is this complete? No, it is not complete. Why? Because it will go into infinite recursion and this function will keep on calling itself till the program crashes. So what do we need? We need a base or terminating condition for this recursion. We need step 3. Base condition means that we readily know the answer for that input. And also, base conditions should be exhaustive. What does that mean? We can start with any input, but as we go down the path of recursion, those inputs should end with at least one of the base conditions. That is what base conditions mean. It is usually reached when our input is becoming very small, or it is reaching close to smallest. So what do we have here as inputs? We have n and sum as input. Now let's say if somebody told us to form sum equal to 0. Now there are n coins and we have to form sum equal to 0. How many number of ways are there? It is 1. We don't pick any coin. Then the number of ways of forming 0 using these coins will be 1. But our sum can go even less than 0, as we can see this from this condition. So what will happen if sum is less than 0? What does that mean? That means what are the number of ways to form a negative sum using some n coins? It is not possible, therefore the number of ways will be 0. Now we have taken care of this input. Now let's come to other input. What happens when n reaches 0? What does that mean? It means you have to form sum, but there are no coins available. So what will be the number of ways in that case? The number of ways again will be 0 because there are no coins available. Now this algorithm is complete and will give us the answer to our problem. But this has exponential time complexity. Why? Because this has a lot of overlapping problems. How? Let's see. Let us say that we want to form sum equal to 5 using these coins 1, 2 and 3. So that means we start in this recursion tree with NOWS 3, 5. Now, how will the tree look like as we progress? If we include 3, we have to solve for 3, 2. And if we exclude 3, then we have to solve for 2, 5. And similarly, if we continue to draw this recursion tree, we will see that we will be solving the same problem more than once. Example here, we will be solving 1, 3 twice. But this was just for a very small input. If this input was large, such overlapping problems will be many. And each of these problems will be overlapped multiple times. That means we will be solving for the same input again and again and consuming our processing power. This is very inefficient. So what can we do about it? We can do one thing. Whenever we see an input, we should calculate for it and store its answer somewhere. And whenever we see the same input again, we should not calculate again. Instead, we should go to our storage and just return the answer directly from there. So we won't be calculating the same thing again and again. Let's see how can we do this. We want to store the information that for a combo of n, sum, this is our answer. And then whenever we want to query for n, sum, we should be able to get the answer very quickly. What data structure will suit this best? It can be map. Why map? Because in map, retrieval against a key is done in big O of one time. Now, we have this map. But for this, we will also have to define what will be the data types of key and value. Now, value is simply answer. Answer is nothing but number of ways, which is an integer. So the data type of value will be integer. What will be the data type of key? The key should be able to represent both these, n and sum. So we can do this by string. We can simply combine n and sum using an underscore and put them in a one string. Therefore, this string will uniquely identify a pair of n and sum. Therefore, a map of string and integer is something that we will use. Now let's see how does our original algorithm change when we use this map. Now we will have another parameter to this method call, which will be a map of string, integer. And wherever we will be calling this method, we will pass this map as parameter. So here also we will pass this map and here also we will pass this map. But Now before returning the answer, we will save this answer in the map against our key. How will we build the key? We can build the key using a separate method which is very simple, just adding an underscore between n and sum. And if before even calculating for an input, we will first check if we have seen this input before. We will check in the map if map contains this key. And if it does, that means we have seen this input before, we have calculated it, and we have put that in map. Therefore, we will directly return from the map instead of going through all of these steps. This will drastically bring down our time complexity. But now what will be our new time complexity? Our time complexity will be big O of n into sum, because for every combination of n and sum, we will have done this calculation exactly once. And similarly, our space complexity will also be big O of n into sum, because these will be the number of entries that we will store in the map. So this completes our top-down dynamic programming approach to solve the problem number of ways to make coin change. Let us now go through the code for the same algorithm that we just discussed. You can also find the link to this code in the description. So first of all, we declare a map. Here we will store the results against our input. Then we call our recursive method. We call it with our initial values, n and sum. And also we will pass to it the coins array and the map that we just declared. In the recursive function, first of all, we write the base condition. The first base condition is when sum is equal to 0. So what is the number of ways to form 0 using any given n coins? One way. Why? Because we don't pick any of the coins, and that is how there is one way. If the sum becomes less than 0, that means it is negative, then there is no way of forming this sum using these coins. So we return 0. If there are no coins to use, but there is a sum provided, it doesn't matter, because we won't be able to form sum since there are no coins, and hence we return 0 again. So this part completed our base condition. Now we build key using n and sum. It is simple. Here we just used underscore between n and sum and returned it. Now we checked in the map if we have seen this key before. That means if we have seen this input before. If we have, then we return the result directly from the map. But if we have not, then we have to calculate. So for calculation, we need last coins value. So last coin value is equal to coins n minus 1. Now what is our answer if we have to include at least one last coin? Then we will call this function with n, comma, sum minus last coin value, and coins and map remain as is. Why? Because now we have to form this sum using first n coins. And similarly, what is our answer for excluding last element? It will be forming sum using only first n minus 1 coins. So we will get this answer as well. Then addition of these two is our answer that we have to return. But before returning, we put this answer in the map against the key. So this completes our top-down dynamic programming approach for the problem number of ways to make coin change for a particular sum. Let us now see our code in action for one of the input. So here we are providing one test case where the sum's value is 4. There are a total of 3 coins. The coin denominations available are 1, 2 and 3. So we want to form the sum 4 with these coins, and we want to return what will be the total number of ways. So let's see what is our output. Our output is 4. So this code works fine. So far, we have been focused on finding the number of ways to make a coin change for a particular sum. But there could also be an extension to the problem. Instead of just returning the number of ways, we could be asked to return the actual ways by which we can make a coin change for a particular sum. So let's see how will we do that. Before even attempting to solve that, let us first see what will our output type look like, because this time we won't be returning integer. Now these are the ways for our example. Now every way we can think of as list of integer, and this itself is a list of such list. Therefore what we will be returning is list of integer, and that means even the answers to our smaller problems will be list of integer for include answer and for exclude answer as well. Now, will we be able to use these answers to form the answer for our original problem? Yes, for the exclude answer, that means we are not including last coin at all. Whatever is the answer, whatever are the list of integer, it is corresponding to this sum. So those ways will definitely become part of our final answer. While for include answer, we have formed sum minus last coin value. We just need to include one last coin value. So whatever is the answer that we got from this smaller problem, we will just put the last coin value as well, in all of those ways. And then those will correspond to forming sum using at least one last coin. So if we add these two lists, it will become our final answer. So in that way, we can also return the list of ways through which we can make the coin change. And obviously, we will have to modify the base conditions as well. So this is how we can solve this extension problem as well.
This is it for this video. If this video was useful to you in any manner, please let us know by commenting below. Also, let us know in the comments what will be the next problems that you would want to see on this channel. Please don't forget to like and share the video and subscribe the channel. We will meet again in the next video with some other problem. Thanks for watching.